little phrase that will help us describe something will be soluble in something else. Like dissolves like.
Polar.
Like dissolves like.
Not polar.
Thank you, Clayton. I knew you'd think with me. Okay, so.
Get your spirit up.
Okay, so that's the solutions. Concentration expression.
Thank you.
Solubility in general. Okay, but solubility, you said it's going to be like dissolves like, but it's going to be obviously based on the polarity, but the polarity is going to determine the what that the solute and solvent will interact with. So polarity will impact how they interact, right? And what are those things we talk about? IMFs, right? So you're going to talk about how solubility and IMFs are then coming together. A couple more big topics. Yeah. So enthalpy. So we're talking about delta H a lot. So we're kind of hitting back on the thermodynamics part of things. Yeah. So I'm going to make this a delta H, delta S, delta G combination there. Okay, so it's all going to be related to thermodynamically favorable processes. One more big topic. Yeah. That's part of the concentration expressions. Colloids. Okay, that's like a small topic. That's like, okay, so, okay, mayonnaise. Got it. We know what colloids are. And ice cream. Okay. What else? So osmosis and osmotic pressure. There's some more properties that relate to solutions that we alter when we add a solute. Freezing point depression, boiling point elevation, vapor pressure lowering, osmotic pressure. Those four are called blank properties. Thank you. Colligative properties. Okay, so this is like basically it. Dun, 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 for the rest of the year, except for like review and stuff in the AP exam. Like we still have a little bit more to do. But we're going to talk about some of the top three today: solutions, concentration types, solubility, and then tomorrow, Monday, Tuesday, Wednesday, we'll kind of hit the rest of this in terms of colligative properties and continuing concentration types. Okay, so let's roll. You guys do this one first. This is a little review question I think you can do without my help. And I'm gonna, while you're doing that, I'm quickly walk around and see our reading guide because I want to see who got some of the questions at the back. You know, the textbook questions. There are like 4 of them. Who got some of those? Who got all of them? All of them? Okay. Okay, we're going to be going through the concentration types today, so I think that will actually make a lot more sense once we get there. Do this in about 30 seconds. You can have there. Maybe want to start me off on the thought process?
540 milligrams.
Yeah. Okay, keep going. Not quite yet. Get that to grams first before we implement, right? So how do I get this to grams? 1,000. So what goes on top? 1 gram is 1,000 milligrams. Okay. And the molar mass is given to us for theobromine. What's theobromine?
Something that does not contain bromine.
No, theobromine. Okay, it doesn't contain bromine, but what's you guys know what that is? No? Chocolate.
It's yeah.
Main composition part of chocolate. Okay, so 180 grams per 1 mole of chocolate theobromine. I don't know.
It's not okay.
Well, why is it called icy hot?
Oh,
it is because it's icy hot. I was going to say it's like an oxymoron, but it's not. It is what it is. Anyway, chemistry. Huh? Is it an automatopoeia?
That's not really an oxymoron anyway.
What's an oxymoron is when it says what it, or
So like
contrasting right? I know chemistry.
Giant shrimp is an oxymoron.
Yeah.
Or like, so icy hot in theory sounds like an oxymoron, other than the fact that it actually is.
But that's like a.
But I guess it is an oxymoron.
Boom.
I was talking about the aroma.
Oh, okay. Oh, okay. I thought I was like, I know what automatic is. How? Okay. So, how chemistry, okay? I know this much English. I know how to speak English. Okay, how do I finish this up in terms of molarity?
Divided by 1.1.
Divided by what?
1.1 liters.
Why 0.1 liters?
Because you have to get the molarity and then you divide it by 10 milliliters.
So you know that now, well, we're not going to actually, we may not have to implement the 10 milliliter part. We know molarity is moles of solute over liters of solution. Solution as a whole, right?
Yeah.
So the solution total volume is 100 milliliters, so I'm going to divide it by 0.1 liters. So I'm just going to multiply by the reciprocal of that. So this gets me to moles of theobromine over liters of solution, because the solution total is what it says in the problem. That is 0.0300 molar, okay? So if that's our case, is that the end molarity? What do we need to do with this? Is that the case, or do we need to implement the 10 milliliters?
No.
Which
Molarity
one?
doesn't matter.
Molarity doesn't matter. What do you mean?
It doesn't matter when you.
It's
Intrinsic.
intrinsic property. Intrinsic. So the intrinsic nature of it means that it's the actual volume of the sample. Doesn't matter. I can have an ocean full, or I can have 10 milliliters of it. The molarity is the same. It's the same ratio of moles per volume. Doesn't matter that I'm taking 10 milliliters out of it. Okay, so it's an intrinsic property. It's an inherent property. It's all just pertaining to the sample, or to the molarity at hand, not really the sample at hand. Okay, so an extrinsic property would be one that the volume does have an impact on the final concentration or not. Okay, so I'm going to go through some of this stuff, give you more expanded explanations on everything you read. So please take annotated notes on your reading guide or other notes. I'll slow down if needed, but some of this stuff is going to be reviewed. We're going to get to concentration practices today in class so that we're all good to go for finishing up that we don't finish in class. Okay, so we have this particular solution forming. You can see that this is really kind of hard to see on some of these accounts, but you can see the water molecules, which are in red here, surrounding this ion. You can also see the water molecules here surrounding this ion. Which is the green ion and which is the blue ion? The green one's up here. Justin. Okay, so which is that one?
Fluoride.
Fluoride. Okay, so you can tell that the water, it's hard to see here a little bit, but the water molecules are facing their what towards the chloride? The hydrogens, right? So this is the chloride, and so this one obviously is the sodium, and what's pointing towards it from the water's perspective? The oxygen. So why is that? Okay. So electrostatic attractions, opposites attract. That has a term, okay? We've talked about 3 IMFs, hydrogen bonding, dipole-dipole interactions, and London dispersion. We've talked about temporary dipole moments, induced dipole moments. This is a 4th type that's actually stronger than hydrogen bonding, okay? It's called ion-dipole interaction. Okay, ion, meaning the ion, the dipole, meaning the water, right? And the interaction between them. Why is that stronger than hydrogen bonding? Right, good. So we remember that it's just the force of attraction is related to Coulombic attraction, right? So we know, and I'm going to write this down here, force of attraction is equal to Q, usually the positive one, right, and the negative one over the distance squared. Well, generally when we're talking about IMFs, we have like a molecule that has a partial negative and a partial positive, right? Well, let's say the partial negative on water is kind of small, and the partial positive on the other particle it's interacting, not an ion in this case, is kind of small. Okay, compare that per distance squared versus an ion, a true ion, which has a full charge, let's say a positive 1. This would be sodium in our case. And then what of water? Partial negative water, which is the oxygen side, right? That over distance squared. This charge product is going to be less than this charge product. So this is a full integer. So that's how the force of attraction is greater for an ion dipole versus something like hydrogen bonding. Are we okay with the quantitative side of that reasoning? Shake your heads, people. Okay, so this is just the quantitative reasoning behind the ion dipole interactions that's actually stronger than hydrogen bonding. I have some pictures on the next slide for you, okay? So, kind of another big picture. Why in the heck is this thing dissolving, but things like lead 2 iodide won't dissolve? Because those are insoluble, right? remember a lot of things with lead. What are our what's our acronym to remember our insoluble layers? So Cash and G's are soluble. What are the insoluble chops? Chops, what are they? Carbonate, hydroxides, oxides,
Phosphates.
and sulfides, right. Carbonates have a -2 charge. Hydroxides -1 charge. Oxides -1 charge. Phosphates -3 charge. Sulfides -2 charge. Okay, how do you think that plays a role in if something's soluble or not? Why am I writing these charges?
Strong charge product.
Okay, so these, like for example, let's do lead to phosphate. Lead to phosphate. Soluble or insoluble? Insoluble, right? You hear lead, you're like, oh, duh, it's insoluble, and we've got a phosphate here. So lead to phosphate, what's its charge product? So an 6. Okay, so lead 2 has a +2 charge. Phosphate has a -3 charge. Charge product is an absolute value of 6. That is hugely attractive to itself, right? Water's not going to be able to compete by attracting it from the outside to pull it apart. Hence why the battle is lost and the product is still insoluble. What is soluble? Something like what? Potassium chloride, which has a +1 for potassium and -1 for chloride. That's an absolute value of 1. Water can compete with that because it can circle the potassium chloride and rip it apart, basically. Okay, so in the end, what's controlling solubility? Charge product. So the charge product, the attraction, that's just for ions, right? Then of course we also have some other things that dissolve that may not be actually ionizing. Okay, so again, on this one, I'm gonna scroll back up here so you guys can see. There are 3 things happening throughout the solidation process. What are the big 3 things that have to happen in order for something to dissolve? You read about this.
The separation of the solute.
So the solute, in this case being sodium chloride, has to be able to separate. What else?
Overcome the IMFs of the solvent.
So the solvent has to, it's all layered together. The solvent has to separate and expand, and then they have to
Interact.
mix together. Right. There are 3 delta H's associated with that process. So what we're seeing here is that this is happening, and I can see it happening in the solution. I can see it's thermodynamically favorable here. This is our enthalpy diagram, and you can see that the delta H for the entire process is endo or exo. Exo, because you can see the reactant starting here. This is a delta H that's negative, exothermic. What can you assume about the entropy of this process? Is the entropy increasing or decreasing? Because you like salt, crazy ions, right? So you're definitely increasing in the disorder. So it's a win-win. Exothermic, delta H is negative, delta S is positive. Those together make a what? Negative delta G, which is what? Thermodynamically favorable. So we just reviewed thermodynamics in a nutshell. Okay, moving on. Sure. Okay, so here, this is the best, I think, the best description of our comparisons of ion dipole and all those other IMFs I just had for you. So I'm going to scroll down to the bottom so you can see that the strength of attraction is based on the distance and the charges. So let's look at this one first. London dispersion, weak attraction. Usually these are going to be because of the low partial negatives and partial positives that can form. And what's forming those? Because it's not a permanent dipole. We call it a temporary dipole. Also going to be generally referred to as induced dipole because something like another molecule can induce a dipole on this one and cause it to have it. Okay, acetone and chloroform. These are going to undergo dipole-dipole interactions, and that's going to be because their partials are smaller or bigger than this one. Right, so I'm just going to say medium here because these are going to be usually between, a small electronegativity difference, not a huge electronegative difference. And so this being partially negative on this oxygen side, partially positive on this side, and then chloroform, the chlorines are on this side, these are partially negative. This is partially positive on the hydrogen side. So there's a bit of attraction. And then the hydrogen bonding is like, boom, we got H bonded with F, O, or N. There's a very large electronegativity difference. So there's going to be a larger partial negative and partial positive. That's going to create that larger amount of attraction. And then you get all the way over here, and now we actually have a problem. We have to consider sodium, but not just compared to one water. there's always for sodium and chloride, there's always 6 waters that surround it in solvation processes. And so there's a lot of attraction going on, which is very, very stabilizing. So this is like a +1 charge with a large partial negative from water over, and all these are a specific amount of distance. And so you can see the force of attraction goes from a low force of attraction to a high force of attraction, which is going to be the stronger force. And whenever you have a stronger force of attraction interacting, that is actually very, very, very stabilizing. So if you stabilize it, it's more likely to occur because it's thermodynamically favorable. Okay, blank faces, not interacting. Some people are writing some stuff down. If you have to draw something for every slide, draw something for every slide. I know some of this is for you, but stay engaged with me, okay? So write something down. Write down one phrase that represents the entire slide, whatever you got to do. I need you to be active with me, because if not, you're not going to remember squat. Okay? So this is a good diagram if you needed to indicate anything else there. And I think with IMS, I think that I've covered enough, gone through enough examples, but we will continue to talk about the impact on physical properties and solvation processes. Okay. Going forward. So how do you know something is going to form a solution? And a solution is a very generic term. A solution is just a what and a what mixed together. Solvent and solute. Sometimes a solvent is an aqueous solvent. Sometimes a solvent is a non-aqueous, so non-polar solvent. And so there we're going to start to see how things can, they're going to not fit our nice little box of what it looks like an aqueous solution. So in this case, we have a mixing occurring of argon and neon. So the nature of or the tendency towards mixing is basically our terms like dissolves like again. And dissolves is also a relative term. And that's going to be, is it polar and polar? Are they like in their bond types or in their IMFs? So they like in IMFs here. And that's going to usually help us decide if something will dissolve or mix. Another reason that something would mix is if the overall favorability of the process is going to be increasing entropy. So increasing entropy and favoring the universe with a delta G of negative. So the potential energy of argon separated from neon is actually higher than it mixed together in terms of the universe perspective. Okay, so these guys, this argon, this is called positional entropy, by the way. This argon and this neon separated, they have high potential energy within themselves. Okay, and so we call that chemical energy. Usually potential energy is referred to as chemical energy and vice versa. And so as you approach the mixing phase, the only reason that's going to be able to mix, one, is because they have similar IMFs. What is the IMF in this case? Right, because these are atoms that they're not polar, right? So they're going to be interacting via London dispersion. And so why would this actually occur? It's simply because the dispersion causes, or the diffusion of the molecules with each other cause increased positional entropy. You guys remember this term? Positional entropy. So think of entropy, right? Entropy is just a disorder, and this disorder is simply caused by not like production of more gases like we did in the past with chemical reactions. We would look at the states of matter reactants, states of matter as the products, and we'd say, oh, 23 molecules of gas made, that's more than we started with. This is just a mixture that's going to be about probability. So like this argon molecule 1, it has the possibility or the probability of being in this location, in position 2, in position 3, in position 4, and so forth, right? All the way down to position 8, okay? But in this case, it has higher probabilities of being in more locations. So its disorder is higher because it has more positions it can take on, because it's not condensed to this little tiny space. So we call that positional entropy because you have more possibilities in your positions. Okay? And that's just related to like statistical probability. So that's one term to start to refer to if you ever need to, because if something increases in positional entropy, that's a positive delta S. And then separately, can you guys see this? I'm scared to cut the lights off, but let me see if this makes any.
We can see it. That's good.
Okay, looking down here, you can tell me why why, if this is a semi-permeable membrane, right here, we have water on this side, we have salt water on this side, sodium chloride and water. Why, if I take the semi-permeable, or even if I don't take the semi-permeable membrane out, why is this mixing?
Has high density.
So it's related to the equilibrium. You're right. It's going to
Maybe
diffuse.
it wants to be the same on each side.
So it wants to have the same concentration on each side, but wanting to have the same concentration on each side means that it's in the end it's going to be more stable, right?
Yeah.
Okay, but why? There's an increased. What kind of entropy? Positional entropy. Okay, so the ions over here are close together. If they can disperse themselves to more disarray, more disorder, they will. And you can also see that the interactions are more stabilizing because here you can see this chloride and the sodium are very close, right? Well, they'll attract, but they're not going to come back together. There's not enough waters around it to stabilize it. In this case, how many waters are around the chlorine?
A lot more.
A lot more, right? So we got like 6 here, and they're attracting it and they're stabilizing it because they're pointing their oxygen, or no, this must not be chlorine. This is they're not really pointing in the right direction, but let's just say they are. They're surrounding and stabilizing. They're surrounding and stabilizing. Okay, so positional entropy is going to allow for us to help explain spontaneous mixing or thermodynamically favorable processes. Okay, this is review. Oh, so in terms of trying to decide or explain when something will dissolve or be soluble, you're just explaining the like dissolves like debate, which is going to be really just regarding their I mass of the solute and the solvent. How do you know which is the solute? If I give you let's say I give you decane and hexane.
Whichever one has less moles.
That's it. Whichever has less impurity. It might not be moles, it might just be grams, right? So lesser is going to be the solute, more is going to be the solvent. That's one note to make. And then what's the word miscible mean? Okay, mixable, or they will mix. So immiscible, an example of immiscible things would be what and what? Water and oil, good. So how would you actually know if you have maybe a more complex compound if they will mix? Things like looking at their functional groups. So things that will mix with water are these functional groups. What's this functional group called? Okay, so philic means loving, right? So water loving. This is a hydroxyl group or just an alcohol. An alcohol will have a portion of its molecule that will mix with water because it has the ability to do what? Hydrogen bond, right? And water can hydrogen bond as well, so it will mix. This is a C-O-H, C-double-O-H. So carbonyl, and what's the example that would exist in? It's on the end of a molecule.
Acid.
There's an A. Aldehyde. Okay. So an example of this would be like an aldehyde. A ketone is going to be this one right here, where you have the C-double-bond-O in the middle, because remember, keys go in the middle of the lock. They're in the middle of the long chain. Aldehydes are terminal. They're on the end of a chain. So so this one and this one will both be able to interact via what? What I'm at. Right, because they don't have an O bond to H. The C is bonded to the H, and the O is bonded to the C. So this is dipole-dipole, dipole-dipole, hydrogen bonding, and water can dipole-dipole because it's polar. So carboxylic acid has the ability to do what and what? Right, the OH group is going to hydrogen bond, and the C-double-bond-O is dipole-dipole, and this is an amine. Where do you find amines? Proteins, amino acids. Amino acids, right? So amines are also like an amide, well, not really like an amide. Amide has a double bond, C-double-bond-O, and then NH on it, but this is going to be an amino acids. And they can interact via what? Hydrogen bonding, right? Dipole-dipole as well, but really the hydrogen bonding is what we're looking at. Okay, so those are going to dissolve in polar solvents. So it's not just like, oh, it's a polar molecule. You also want to be able to describe which part of the molecule is going to be actually interacting with the solvent. Nonpolar things are going to interact really, really well with nonpolar solvents. What's a great nonpolar solvent? Hexanes, okay. What's the formula for hexane? C6H14, so you're doing 2N plus 2 in your head, right? Okay, or what's the cyclic one? Benzene, what's the formula for benzene? C6H6. So that's our resonance structure we drew, like times like this.
Like that.
It's an aromatic hydrocarbon, so it can form. It's very volatile. What's volatile mean?
It is able to become a gas from liquid state.
Okay, so it can do that, but benzene is a good solvent as well. Okay, back with me. Molecules that have both parts of these, so hydrophilic and hydrophobic regions, they're going to interact with both types of solvents. Sometimes what we do in chemistry is we make mixed solvents. We'll make ethanol water, because ethanol has a large nonpolar component, and water is going to be the polar component. It will bring things into solution better. And that's specifically because a lot of times if things come out of solution, the reaction will stop. It's useless. We're wasting compounds. It's not green chemistry. Okay, so just make sure you're familiar with the hydrophilic and hydrophobic regions, and that they can actually interact together in a different within different types of solvents. Okay, so these are the just to kind of recap in terms of, I have to remember really what I want to tell you here. Oh, that whenever we talk about mixtures can be solid-solid, liquid-liquid, gaseous-gaseous. So a gas-gas mixture is going to be, based on its IMF, some, but more than anything, if they can't get together, they won't mix, right? And what's going to cause something not to be able to get together in a gas? Things that are really heavy, like carbon dioxide, they are very heavy, 44 grams per mole. It's very dense. Versus something like neon's what? 20 grams per mole. So things that are less dense will float, things that are more dense will sink in a gaseous mixture. So they're able to better mix if they're similar in their molar mass in that respect. Okay? Give me a thumbs up or a smile or a wink. I mean, whatever you guys do. Okay? So liquids are going to be more soluble, and that's a solvent-solute interaction again, and that's definitely referring to our polarity that we've been kind of talking about this whole time. Oh, I didn't erase this. Well, let me just erase this part. You guys can tell me what this is. And so, in the solid-solid mixtures, an example would be like an alloy, and you took notes on alloys. What are two types of alloys? Maggie?
Interstitial.
So interstitial.
Vital.
You know, like you guys know what interstitial fluid is?
Yeah.
Where's Chitra and Han?
Fluid in between cells.
Cells, right? Interstitial fluid is stuff between cells.
You said that because they take AP Bio.
Yes, and people in anatomy should know this. I'm trying to think of who else in anatomy. Okay, I only know a couple of guys in anatomy. Okay. So interstitial alloys have what's their composition like? Okay, so atoms usually atomic nonmetals in between larger cation cores. So this might be like iron, so Fe, iron, and then there's a little carbon right here. Iron, carbon, iron, carbon, iron, carbon, carbon, carbon. What have I just made? Iron, carbon. Steel. Okay. So that alloy is a mixture of two solids. This one, where I've substituted a different, larger, similar sized atom for iron, let's say iron versus copper. I don't know what that means. Let's do zinc and copper. Okay, so zinc, copper, because you can see they're similarly sized because they're right next to each other. They're on the table. What have I made? Brass, right? And brass is not an element; it's an alloy. So this is what kind of alloy? Substitutional alloy, right? So interstitial, things that are small, go between the interstices or the holes between them, and then substitutional. And then when you get into geology in the real world, then you'll see alkali feldspars. This is an example the AP chemistry curriculum requires me to tell you about. Okay, alkali. Give me some examples of alkalis. Potassium, sodium, I heard. Okay, an alkali feldspar, which is a rock with alkaline or alkali metals in it, potassium and sodium, and these are going to be like more mineral composition. So this is actually how every gemstone is made. It's just a mixture of different solids. Okay, except for diamond. Diamond's the same thing. Okay.
I really want you to explain that. Bear.
Okay, so guys, these are not polar bears. So we call them nonpolar interactions. Oh, it's okay. Get all those two non-polar bears.
Oh.
And so, non-polar.
Non-polar. Why they were non-polar, but now I get it.
Yeah, it's because they're grizzly bears. Okay, learn something today. Okay. So, I know you're wondering, guys, how does soap work?
What?
It helps the
That's
water,
what-
and why are you ruining it? Pictures first. Okay, so
Nobody knows.
I know.
We're
I know you're into
Magic
Chem.
cleaning stuff.
Tell me what this tail means. What's this wiggly line? What is it?
Non-polar.
Well, what is it?
It's a carbon chain.
Thank you. Carbon chain, carbon chain, carbon chain. How does it interact? London dispersion forces. And what is it? What is London dispersion going to interact with if you're cleaning something? Oils, dirt, fat, mayonnaise on your shirt. Okay. So dirt, grease, fat, oil. Okay, dirty stuff. And then what does this interact with?
Water.
This is the polar side, so this is going to interact really well with water. So lawn detergent, soap, and all that jazz will basically attach to a water molecule, and its tail will attach to some dirt, and then they come together and they go down the sink. That's it.
Wow.
Thanks, guys. Look, it is complicated. It's called emulsifying agent. See how hard that is to say? Okay, and so emulsification, emulsifying agent, is the thing that has both polar and nonpolar components on it. Okay? So what's the emulsifying agent again?
Oh, it's the dissolved fat. Stuff like that.
But how do you know from a compound perspective? It has both what and what on it.
And the polar and non-polar stuff.
Right, so the hydrophilic and hydrophilic functional groups, for example. So you're right, somebody mentioned earlier that it reduces surface tension because water, it'll disrupt its hydrobonding nature because it's going to be interacting with the hydrobonding and causing a nonpolar component to be exposed to it so the water can't get together, so it limits its surface tension. Okay, surfactant is another word for that. Moving on. Wink, thank you. Okay. This is the part that was in your reading that was kind of more new for us, but Clayton's already kind of exposed this to us. There are 3 steps to a mixing process. I know you didn't know this. First thing has to happen. The solute has to overcome its interactions. Well, that just basically means you need to separate the solute. Separating the solute is an endothermic process. We understand why. Okay, what does this mean to you?
Takes energy.
It takes energy to
Break.
break bonds, right? Whatever the bonds are, covalent. It's going to take a lot of energy. Ionics is overcoming the lattice energy, and so it's breaking that bond, the ionic bond. So that's going to be an endothermic process. Separation of solvent molecules, for example, water or benzene in this case. I got 2 examples here, water and benzene. Water and water interact via hydrogen bonding. We're not breaking bonds, right? Horrible phrase to use for intermolecular forces. We are overcoming IMFs. Okay, so overcoming IMFs is going to be what's happening. It's still an endothermic process because you still have to put energy into doing that process. What IMFs would be overcome in this one? Why? London dispersion forces versus hydrogen bonding, whose endothermic process can be at higher magnitude. Right, so that you're going to know the delta H, this is called delta H2, by the way. This is delta H2, this is delta H1, because it's referring to the first step, second step, and this is third step. The delta H2 for water is greater than delta H for benzene. Whenever they come together, there are attractions. That attraction, the magnitude of the attractions will refer to the amount of energy released. Because remember, whenever 2 things come together and they're more stable, they're releasing that extra energy. So they release energy, which relates to a more stable or more thermodynamically favorable product. And that product is just a mixed solution in our case. So the only reason something would ever make a solution is if, in the end, the H of solution is negative. So delta H solution should be negative because that is the stabilization process, is whenever you release extra energy. Well, how in the world is delta H solution going to be negative? What are the magnitude differences between these? So delta, you're right, the sign is negative, right? So you told me that this, okay, so you're saying really large. So you're saying this mixing process is very negative, very large negative. This IMF overcoming and the solute being overcome, those have smaller positive numbers. Okay, so which relates to the energy that's being put into the process. Okay, so the way that this would occur is if that delta H3 is a very large negative number, right? Can you think of an example where a solution, when it forms, does not feel warm to touch? Cold packs, right? Okay, so I just said, huh? Ammonium nitrate. So we all familiar that ammonium nitrate is one of the only things is that's used in a cold pack. Okay, it's one of the only things that absorbs energy from its surroundings. How in the world is that still making a solution? I just said most of the time the solution process is exothermic, because this relates to our whole debate of negative delta H, positive delta S. That's going to create a negative delta G, which is thermodynamically favorable. If the enthalpy is endo, how would it still be forming a solution?
Requiring energy to break it on.
Well, it is still doing that. Like you're right. It's still requiring energy to break this bond. The delta H3 is just not as negative. So in the end, for ammonium nitrate, this is positive. But if that's positive, most of the time that means a solution won't form, correct? That's not favorable, unless entropy is incredibly positive, right? So what's happening here for ammonium nitrate? We already talked about that. Delta H being positive is not so favorable. But for ammonium nitrate, the delta S, the entropy, is very, very positive. So if this is very positive, that disorder is more significant in that case than the enthalpy, so the heat compositional part. So ammonium nitrate, NH4NO3 solid, going to aqueous form, will occur because it is thermodynamically favorable overall, because the entropy is much greater than the amount of heat that is taken and absorbed, so the delta H part. And that debate is encompassed in what formula? Gibbs free energy formula. So equals delta H minus TOS. And so this value is a small negative. This value is a small positive. This is a very big positive, so when you subtract it, it's still a negative number. Math. Moving on. How are we doing? Good. What time is it? 74. Okay. So attack of the water molecules. You guys can see how this works. Water molecules attack. And I want you guys to tell me, based on the picture, based on what you know, what is the IMF that's interacting? That's allowing for that process to form. Ion dipoles, right? So ion dipoles is the one that's more significant than hydrogen bonding. And then we just talked about that. Great. And then we just kind of talked about this. Let me just make sure we're all good here. Yeah, we did. So we talked about how this value here has to be greater than these two corresponding values for the delta H solution, the exothermic overall. And why is this process occurring overall? The disorder is also increasing. This is a lot of stuff from your reading guide. Okay, this is kind of a more significant terminology debate here. What is a good word for hydrochloric acid going into solution? Okay, so either one of those words. Ionize and dissociation are good terms for that because they literally make ions, right? So HCl going into solution makes H plus and Cl minus. Even you can still use that for, like, for example, acetic acid. But what's different here?
Not 100%.
Right, we have a double head arrow to make H plus and C2H3O2. So dissociate and ionize are still true for that. What's another type of compound that you would use ionize for? Or dissociate? Ionic compounds, right? So whenever you say the words ionize or dissociate, please make sure it's very specific to these types. Whenever you use the word hydrate, what does that sound like?
Water.
Something in water, right? So hydrated means that the particles hydrated means surrounded by water. That's all hydrated means. Surrounded by water. So what kind of compounds can you use that with? So polar, and what else? Salt and sugar. Sugar is what? C12 H22O11, that's sucrose, right? Sucrose is a freaking covalent compound, not an ionic compound, right? You still can use the word hydrate, but don't use the word ionize or dissociate. You can also use the word dissolve for sugar, but what do you mean by dissolve?
Dissociate.
You do not mean dissociate, so what do you mean?
Drown my water.
Surround by water, okay? You mean it may not be just water though. Dissolve is non-solvent specific. Hydrate is solvent specific. Yeah? This means to surround with water, so this is just like, I say polar compounds, but don't forget that these molecular compounds, which are have polar subgroups, can be hydrated. They can also dissolve, but this is non-solvent specific. So, for example, chlorine gas can dissolve in benzene, right? Because it's nonpolar, but can water dissolve in benzene? No. Okay. So the word dissolve is a very horrible word because it's not very specific. And then the word solvation is that you can just have a solvent interacting with solute. Not very specific either. Okay. So if you want to be more specific, use the word ionize or dissociate and hydrate. Okay. One more piece here. This is the part where we talk about the opposite of lattice energy. Okay, what's the opposite of lattice energy? So lattice energy is you take two ions, you take the two ions and you form a crystal. So there's crystallization energy. So when you dissociate the crystal, it's usually called crystallization energy. And you saw that, some of you guys saw that in your IMF multiple choice yesterday. Okay, so first off, this is, I'm trying to hit all the highlights here, okay, because this first part's kind of long. The hydration part of things is just whenever you're not considering the mixing, you're not considering the lattice energy involved, which like H1 being the solute interaction. If you have to overcome interactions on a solute, if it's ionic, you're considering lattice energy. So you're just talking about how water's surrounding the crystal or the solute, whatever, maybe molecule or not. And so a lot of times that has its own special formula, which is delta H2 and 3. This is for the solvent IMFs that are being overcome, and this is for the mixing process. Noticing that we're not really involving the solutes breaking apart. And so we call that delta H of hydration. I'm going to come back and finish these because these are a little boring right now. Can we do some math?
Yes.
Okay, let's go to molarity, molality stuff. So we'll do the solubility stuff later too. Okay, these are the big 4, 1, 2, 3, 4. Normality we don't really calculate, but we know it's here. Do I need to go over these equations before we start? This was in your reading last night. Okay, that's actually the one I'm going to go over. Okay, so mole fraction is going to be here. Okay, so molarity, before you write this down, okay, molarity's units are what over what? Moles of solute. So now I really want you to be specific. Moles of solute over liters of solution. Solution is a combined solute solvent, correct? Okay, molality. Right, okay. Moles of solute. Let's make sure we're all good there. Molarity is moles of solute over liters of solution. Molality, which is little m, is moles of solute over what? Of solvent, right? Not solution, not solution. Mass percent. And mole fraction is very similar, but mass percent is just taking your grams of your solute divided by your grams total, and that's of solute and solvent, times 100 because it's a percent. And then mole fraction is like mole percent, except we're not doing it multiply by 100 at the end. We're leaving it as a fraction, which we actually do express as a decimal here. For this mass percent one, is there a unit? Right, it's percent is the unit, I guess you could say, but really it's grams over grams and grams over grams cancel. So you can imagine that mole fraction, similar story, doesn't have a unit. Yay! Like one time where unitless is totally fine. So if you have moles of your solute, generally it'll tell you what it's actually asking for. So it'll say like XA to say moles of A or moles of solute over all the moles of solution. So that's going to be solution, which is solvent moles plus solute moles. And then we don't multiply by 100, so it's not technically percent, but we also don't leave it as a fraction this time. We report it as a decimal. And so if we report it as a decimal, let's say I have two things in my solution, a solute and a solvent. What will the mole fractions combine to equal? What if I have XA for my solute and I have XB for my solvent, if I want to find its mole fraction, this is a number, this is a number. What happens if I add these two numbers together? What will they equal? 1, right? Because a fraction is just a decimal. So like, let's say this is 0.5, this is 0.5, they should sum to 1. That's how you'll know if you're right, if you need to verify mathematically that you are on the right track. Okay, let's do this problem together. There are two problems that regard molarity and then mole fractions. I'll come back to some of this. Okay, these are your two questions. You guys actually go ahead. Try it. Let me see what you remember. I know you can do the first one. Let me see what I can see for Monday. Nathaniel, how are you getting started on number 1?
25 grams.
Okay, so your question is molarity, right?
Yeah.
And what's the question? What does molarity actually mean again?
Moles.
Moles of what in this case?
So,
What, but who in this case, sorry? So magnesium chloride and over what? Right, so liters of solution. So sometimes I like to define what we're looking for at first so you don't forget that later on down the line as you're walking through multiple calculations. So you're right, start with your 25 grams of magnesium chloride. What's the molar mass of magnesium chloride? Somebody? What is it? 95.2? Yeah, okay. So 95.2 grams of magnesium chloride is 1 mole of magnesium chloride. Okay, we can stop here and get moles, right? Or continue and just do what?
Divide it by the.
And what's our liters of solution? 0.45. And that's okay, or you can just take your moles and then divide by 0.445 liters. And that gives me what, guys? You guys are calculating, because I don't have my calculator. What is it? 0.58? And I would do 0.5. I need 3 6/8. 3. 5.834 molar. Okay, so the solution is 0.584 molar magnesium chloride. That one's easy. Okay, let's go for the next one. Solution prepared by mixing 85 grams of hexane and 45 grams of decane. What's hexane? Formula. Hexane is C. Is everybody clear on how to get your formulas for anes? Alkanes. 2N plus 2 is how you get your H. Decane is what? C10H22. What did it say? 85 grams of this and 45 grams of this? What it said? Yeah, okay. So calculate the molality, mole fraction, and mass fraction, or mass percent in this case, okay? So you guys tell me, how am I approaching molality? What am I looking for first? Okay, so who's a solute? Right, so does everybody's clear? This is the solute here. If you have to make your own decision, you look for the lesser amount. And this is considered the solvent. Okay, so molality, here we go. Molality is moles of what? So decane, right? over kilograms of, right, so you notice that you're doing solvent here, not solution total. Okay, so moles of decane would be 45, so let me calculate some more mass. 45 for decane times 1 mole of decane over what? 0.29. Okay, so that's decane. Can you tell me the moles of that? Because we're going to need that later on. You did take that divided by that. Oh, I have I want to round 0.317. Okay, so that's moles of decane. And you're going to want to label these 100% of the time because sometimes you'll forget which moles is which. It's to your benefit to do this. All right, are you guys writing this example down? Okay, you might want to so that you can do your homework later without me. Okay, so this is our moles of decane. That divided by kilograms of solvent, which is how many kilograms? Right, 0.085 grams, bounce back to 3 decimals, right? Gives you kilograms of hexane. Just want to make sure I'm writing it right. Okay, so then 0.317 divided by 0.085 is what? What is it? So it's 3.73. I'm going to write this like this for a second. 3.73 molal, or molar, or molality is referenced as molal. And that's molal C10H22. So there's the molality of decane. Next question was, what's the mole fraction? How do we find the mole fraction?
45.
Say again?
45.
No, it's moles.
Right. So this is mole fraction. X is the descriptor of mole fraction, and you're describing the mole fraction for decane in this question. So you should label it like this so you remember what you're referencing. So you're doing moles of what over moles of what? Right, so solute in this case is decane, and that's why I had you guys calculate this squared off so that you don't have to recalculate again because you've already done that part. 0.317 moles of decane over what? Which you've not calculated, right? We haven't calculated moles of hexane, right? But we're going to have to put both the moles in the bottom, right? It's a summative mole. So I'm going to go ahead and write 0.317 moles on the bottom plus hexane's moles. So what's hexane's moles? What was it, 85? 85 grams divided, and 1 mole of hexane is what? 86.1. Oh yeah, okay, 86.18 is fine, okay. So how many moles is that for hexane? 988, but I'm going with you. 9863. Tell me it's making real sense. Okay, so that's our hexane, that's our decane, add them together. And it's nice for you to write out your work to the side so that you don't have to keep redoing your work and you don't have to keep wasting time, really. So take your fraction, and that should be 0.243 for your mole fraction of decane. What's your mole fraction of hexane? You have 10 seconds. Complete me. Fraction of hexane.
0.9863 over.
No, don't do the math.
24.3.
So you're doing in your head 1 minus 0.243 because 1 is the total mole fraction. Subtract that. So what do you get? 0.757 sounds like that's right. Okay, that's mole fraction of hexane. Don't forget, you can do mole fraction very quickly once you have one of the parts. And then lastly, the question was mass fraction or mass percent. How do you do it? So you use what? You use grams all the way, right? So you're going to do whatever what? Grams of solute. So mass of, what was that again? 45
grams.
45 grams of decane over, what is that? 120? So 120, 130? 130 grams of total. And you can get fraction without doing the mass percent by not multiplying by 100. So the the mass percent would be, the mass fraction would be 0.645. That's in reference to decane. What's the mass fraction in reference to hexane? 1 minus that. 1 minus that. Which would be 1 minus that. 0.346. Okay, dears. I'll finish the ocean my day. Fill your packet. Go to the day one solutions. I haven't done every example known to man, but I think that you can approach these. There are 5 questions on there. And, okay, there's 5 questions, but they have A, B, C, D parts. So, 5 big questions. Taking your molarity to using density, you go to mass percent, you go to mole fraction, you go to molality. You have 20 minutes right now. I need you to ask me questions in class so I can make sure I do enough examples for you before you go. Okay?
What question are you looking at?
Looking at practice solutions day 1.
Oh, okay.
You see it?
Yeah.
There are 5 questions. Am I right? Yeah. Yes? Okay, please right now practice as much as you can. Skip around if you need to. I need to make sure I do as many examples as you need. Because I haven't done any using density, but what is the only value of density to us? It helps us convert from what to what? Density.
Grams per milliliter.
Okay, it's grams per milliliter, but it helps us convert between what?
Water is grams.
Not just water. Everything's got a density, not just water. Okay. It helps us convert between volume and mass. There is no other conversion between volume and mass, right? There's only mass and mass and moles, atoms and moles, and volume and moles, but there's no mass and volume, and that's where density comes in to help you convert. So please start on the first one, and I'll help you from there if you need it.
Good.
I know, Alex must be nice, man.
Almost 3 days of school.
So you can ask me questions.
Oh, okay. I just started.
I'm doing these with you so I can make sure that you have enough time.
You only want us to do one at a time.
Right now. If you have to, 1 point to note, okay? If it doesn't give you a volume, but it gives you molarity, break the molarity into its 2 components. What's the molarity in this case, or what's the components in this case? So there are 3.75 moles of H2SO4 per 1 liter solution. So if you need to take that 1 liter solution and do something with it, you made that assumption, you have the moles that are equivalent to it. You can use that 1 liter to go with where you need to go with it. You can basically assume there's 1 liter step. Or are we doing mass percent one?
Not good.
Not good. No, this is the one I thought you'd need help on. How have some of us started first? How? Okay, you can go to molarity. You don't need to go for molarity moles if you split it like I said. You should be able to just take your moles that you've decided upon and go with it, okay? So I'll help you guys out on the first one here. This is problem solving basics, right? You guys are really good problem solvers. You know so much, you know too much for your own good sometimes. Okay, so this is 3.75 moles of sulfuric acid per 1 liter of solution, right? Use these two pieces separately. This you can get from moles to grams of H2SO4. This you can get to what with? How? Start me off here. So I'm going to use 1 liter of solution. Right, so let's take our liters to milliliters, what you mean, right? Liter, 1,000 milliliters, right? So that 1 liter is 1,000 milliliters. And don't forget to label this solution. I know it's stupid. You're like, I'll remember it's solution. You won't. You forget what you're talking about, okay? So, and then tell me what next. 1.23 grams, 230 grams of solution is 1 mil per 1 milliliter. So this is where we incorporated density, get from volume to mass, which is a valuable tool. This is 1,230 grams of solution. So this is mass total of solution, right? That's going to go to the denominator of percent by mass. This 3.75 moles of sulfuric acid, 98.076 or something like that. 0.08 grams of H2SO4 per 1 mole of H2SO4 gives me about you can see it's about times 100, right? So you can guess me it's a little under 400. So you can make sure you're doing it right. 367.78 grams of H2SO4. Okay, so this is the part over the whole as you mass percent. Right, that's our solute. So you're taking this. Oh. Right, well, no, this actually, the solution, good point. The solution is already summative. It already has the solid composition together. So we're going to use the 367.78 divided by 1230 times 100. That'll be your mass percent. Okay, so I'm just helping you dissect it because I know you know how to do each part. It's just you haven't started off with molarity yet. So over 1230 grams times 100. This is solution total. This is H2SO4. That gives us, what is it? 29.9%. Great. H2SO4. What's the next question on here? Okay, so I think, mole fraction. No, you can do mole fraction. No, you can't. Okay. I know you can do mole fraction numerator. What's the mole fraction in the numerator? 3.75. Is everybody with me? That's H2SO4. Mole fraction in the denominator is solution total, right? Well, if you have the grams of solution total, can you get to moles of solution total? But you don't know the molar mass of the solution because it's not a compound, right? So you have to segment it and then put it back together. So here's what we do. You know the mass of the solute. Therefore, you know the mass of the solvent. What's it? Yes. Okay. Oh my God. Are you serious? You're not serious. This is easy.
Yeah,
this is
okay. Easy, but I wouldn't even
but once you get one under your belt, you will think of these from now on. Okay. So 1230 is the solution total, and you subtract the 367.78 grams of solute. You will get these grams of water, and this is an aqueous solution. I'm not sure if it stated that. If it doesn't say it's a non-polar solvent, it's aqueous solution. So I'm mapping it up with you guys. 1230 minus 862. Dang it, Maggie. 62.22. Okay, so that's our grams of water, and you can then take that to moles of water, right? So I like this calligraphy thing. Okay. 1 mole of water, 18.02 grams of water, gives us, Maddie, you got it? What is it? 47.85 moles of water. Okay, and circle and label, because you will forget what these numbers are representing. Okay, then how do you do mole fraction? So mole fraction of sulfuric acid is 3.75 moles. Where did I get that? Initial of sulfuric acid over total summative moles. So 47.85 moles plus 3.75 moles. And that will give you a fraction such as, I don't have the math in front of me, guys, so 0.0726. And that's the mole fraction of sulfuric acid. So the mole fraction of water is going to be, 0.9284. No, 74. 9, yeah, that other part. Okay. Last one, let's do this. Let's just finish this together. Molality. Now, recap, look through all your work. What do you already have for molality?
Moles of solute and grams of solvent.
So you've okay, so if you've labeled everything thoroughly, you don't have to recalculate anything. So molality would be moles of the H2SO4, which you already have on your paper someplace, and the kilograms of water. And like you guys said, you had grams of water here. You just need to convert that to kilograms. So it's a big piece of, it's like a 1,000-piece puzzle, and you're putting it together in like 5 different ways. Yay. Okay. Are you guys comfortable doing the rest of these? Maybe? Okay. Remember, if you have to make up a volume, you make it up and you keep it the rest of the way because it's equivalent to whatever you've associated with. Like I made up a liter, which is 1,000 milliliters. We're just representing concentrations in as many ways as we can.